Now let's go beyond our solar system and explore the world of exoplanets. This is exciting science. The first exoplanet was only discovered in 1995 after centuries of speculating that our solar system shouldn't be unique. Now finally we have evidence, and we have cataloged over 4,000 exoplanets, an incredible field that's matured very quickly. Here's how quickly it happened. The first detection, 51 Pegasus in 1995, led to the award of a Nobel Prize quite recently to the co-discoverers based in Switzerland. And here on a logarithmic scale you see the mass of the exoplanets. The first ones to be found were around the mass of Jupiter, 51 Peg, about a third Jupiter mass. So these are not Earth-like planets, these are gas giants, and you can see that for most of the first decade they were mostly gas giants being found. But look how the detection limit and the minimum mass and the smallest objects found has steadily marched downward over time. Remember, this is a logarithmic scale. This is pure prowess in astronomy observing technique, precision spectroscopy and precision photometry applied to a very difficult problem. And you'll see that in 2011, 2012, for the first time, we discovered an Earth-massed or Earth-sized planet. Now it's almost routine to discover Earth-like planets. But again, the first one was discovered less than a decade ago. And again, many are still massive. You can see that even in 2011, most of the planets being found were Jupiter mass or Neptune mass. So there are many gas giants out there. But the ones inevitably of interest when we consider biology are the ones that are like us. Here's a sense of the crescendo of exoplanet discovery since that first discovery in 1995. And here we get to see one of the multi-planet systems that has been discovered quite recently, indicating they are not just single planets, but full solar system analogs like our own. Here we can visualize the various detection methods. The enormous crescendo of discovery in the last decade was caused by the Kepler satellite, a 1-meter telescope that used the transit method, where when the planet crosses the face of its parent star, it dims the light briefly for a small amount, and then that repeats every orbit. Kepler was able to look at transits of Earth-like planets crossing the face of Sun-like stars, making 1/100% dimming of the light just for a few hours, and found many planets that way. The first set of planets were found by the radial velocity technique, which looks at the Doppler shift of the star itself. The planet is not seen, but it's tugging on its star, and the wobble of the star is betrayed by a radial velocity variation with the same period as the orbit. You can see in this montage that on the upper right, the transit technique finds the most planets by that occasional dimming of the light. Radial velocity finds the next highest number of planets. A much smaller number of planets in the lower right are found by direct imaging, where you black out the light from the bright star and try and see the planet directly. Also, microlensing has been a fairly successful technique and can find very small planets, smaller even than the Earth. When you have both mass measured by the Doppler method and size measured by the Kepler transit method, then you can get the mean density of a planet. And here we see the mean density plotted relative to different kind of ingredients. And so this mean density does not give a unique model for the planet, but it does allow you to distinguish between the composition of something that's like Jupiter and essentially gassy and something like the Earth that's essentially rocky. There are even some worlds that have density very close to that of water and are speculated to have 10 or 100 times the amount of water as all the Earth's ocean. These are true water worlds, even more extreme as a water world than the Earth is. Here's a montage of the Kepler transits. You can see the planet superimposed on its parent star. Most of the stars are sun-like stars, but Kepler also observed dimmer red dwarfs and brighter, more luminous blue stars. If you want to see the orbits, Kepler, of course, measures the orbital period as well as the size of the planet. And so with the Kepler data, you can make an orrery of these planet orbits and also see the multi-planet systems that Kepler has discovered. It's a good way of visualizing what is a vast amount of data. Let's look at the exoplanet populations that have been outlined now that we have a large number of exoplanets in the bag. On the horizontal axis, you see orbital period on a logarithmic scale. And on the vertical axis, you see the size of the planet. So the planets near the top and on the top left are hot Jupiters. They're Jupiter mass and size planets that are very close to their parent star. A number of these were found early on, and they were very confusing because no one could understand how a Jupiter mass planet could have formed so close to its star. It turns out they didn't form there, but they migrated inwards. So one of the results of this exoplanet research is the realization that planets don't always stay where they form, or after they form they can move. Solar systems can rearrange themselves, and we actually think this happened in our solar system too. As more data is accumulated, you get to look at longer orbital periods. So with 7 or 8 years of Kepler data, we can now find gas giant planets in more typical orbits that we see in our solar system, Jupiter with a 12-year period at 5 astronomical units, for example. In the middle, in the blue oval, we see fascinating worlds that are like Uranus and Neptune. They're ocean worlds and ice giants. Some of them are warm enough because they're close enough to their stars that they do have liquid oceans. Massive oceans, because these are bigger planets than the Earth by a factor of 10. And then in the yellow area, we see the rocky planets. On the far right of this shape, you see the position of the Earth with an orbital period of about 360 days and Earth size. And then there are a lot of planets like that, but many are actually closer to their stars than the Earth. And at the extreme hot end, in the green area, we have lava worlds. These are small planets, Earth-like in size, Mercury or the Moon perhaps, that are so close to their stars that their surfaces are literally still molten. And that's the end of this topic.